Steve, take it away.
Can you all see my screen properly?
Yes.
Wonderful.
Maybe you
Thank
want to
you.
do full screen.
Okay.
Yeah, that's much better.
Yeah,
Much better.
perfect.
Yeah.
Okay, so hi everyone. Thank you so much for joining us today to listen to our presentation on our accessible heart health kit. This is our team. We're Agustin, Ahana, Akshaya, Ash, and I'm Fifi, myself, Francesca, and Tamana. So we're from Argentina, India, and Ghana. Um, we're going to go through a little bit of the context. So cardiovascular disease is the leading cause of death worldwide. A huge number of people died from CVD in 2022, 19.8 million, and over 75% of these CVD deaths take place in low and middle income countries. Um, this is partially due to the fact that cardiovascular diseases can be prevented by addressing behavioral and environmental risk factors, which is very difficult to do in vulnerable contexts when uh, structural stressors are present, pollution, and it is very hard to change people's diets or physical activity um, habits. And given that we have found that no system in the market combines the main factors we're looking at, which is low cost, accuracy, signal quality feedback, primary care usability, and offline capabilities, we have put it upon ourselves to design kind of a low cost, robust, and accessible heart health kit that works in low resource and vulnerable settings, specifically relying on no connection, no connectivity, no stable electricity, or the presence of a specialized professional.
So for our project, we considered two sensing technologies, the ECG and PPG. So ECGs measure the heart's electrical activity through skin electrodes, and it's currently considered the gold standard for detecting arrhythmias and extracting information such as heart rate variability, thus making it more reliable for early cardiac risk detection. However, it is slightly harder to use and it requires correct electrode placement and somewhat more complex hardware. PPGs, on the other hand, use optical sensors to detect changes in blood volume. It's cheaper and easier to use since it doesn't require those electrodes, but it's more sensitive to motion and less reliable for detecting conditions like arrhythmias. And since our goal is accurate early detection, we chose an ECG as our primary sensing technology because it offers stronger clinical reliability. However, this raises an important question. Can a primary healthcare worker with limited technical experience obtain a high quality ECG, especially in low resource settings? Thus, our project aims to address this by developing a feedback system that guides correct electrode placement.
So for this purpose, we designed a very simple prototype. This has an AD8232, which is a very simple analog module for ECG acquisition. Something that is specifically interesting about this module, it has a built-in lead-off detection, which means it can detect whether the skin electrode contact is good. And we used a simple Arduino Nano for rapid prototyping and some standard 3 electrodes for this configuration.
Okay. So I'm going to be talking about the quality signal acquisition. So number one, we wanted to actually just understand the electrode placement and what exactly needs to be done right. So we were first looking at skin contact, and we found that 70% of the if 70% of the area is contact is covered, then it lowers impedance and it cuts noise, which is less than 5 kilo ohms. And in terms of placement, there's a lot of research for the 12 lead ECG, which is the main one, but the one that we're focusing on is a 3 lead ECG electrode placement. So over here in the 12 lead ECG, we found that a margin of less than 1 centimeter is critical because it reduces the amplitude distortion by 10 to 20%. However, because our model is not the same, we don't have accurate statistics for this. Additionally, we also found that placement varies from different kinds of patients and different kinds of body types. So for females, it's very important, especially, again, this is for the 12 electrode setup, but V4 and V6 should be positioned under the breast tissue and not on top of it to avoid signal attenuation. And lastly, we also were thinking about the feedback loop. So currently, to understand exactly where correctly the electrode should be placed is not something our software can do, and it's not in the prototype right now. However, I think we will talk about this further. Sorry. Yeah.
So the processing pipeline begins by importing the ECG recordings from the CSV files and extracting the ECG LO plus and LO minus signals. The ECG signal was first cleaned and normalized to remove the scaling differences and to prepare it for analysis. We had a filtering step in to apply that was applied to reduce the baseline drift and the noise in the waveform. We tracked and detected the heartbeats by identifying the R peaks in the ECG signal, and these corresponded to the ventricular depolarization. By using these detected peaks, the system was able to calculate the heart rate and estimate the signal quality using the statistical noise-based metric. So the pipeline also checks the LO plus and LO minus lead off signals to determine whether any electrode has lost contact with the skin. And this process data, and it only takes about under a minute to get the signal feedback. So the process data is then displayed through the visualization dashboard that we'll be showing, which has the ECG waveform, detected peaks, heart rate, signal quality, and electrode status. So the signal processing was implemented using Python in Google Colab. So we use libraries such as Pandas and NumPy for data handling and numerical calculations. We used Matplotlib and Seaborn for ECG visualization. And ECG filtering and heartbeat detection were performed using NeuroKit 2, which provides specialized functions for physiological signal analysis.
In terms of pre-processing, we feed the signal from the sensor into the NeuroKit 2, which is a Python library that cleans the raw signal and it helps to detect the heartbeat. And it detects components like the P, Q, R, and S and T waves. So on the left side, that you can see there are three plots. The top one is the raw signal, which is coming directly off the sensor. And the middle one is the hello, am I audible?
Yeah. We're just trying to
okay.
change the illumination in our room so that we can see the
all
screen
right, all
better.
right.
Awesome.
Sure. Okay, so I'll resume. So on the left side, you can see the three plots. The top one is the raw signal, which is coming directly off the sensor. And the middle one is the sort of the clean signal with the detected heartbeats marked in red. And at the bottom one, you can see the heart rate over time, where you can see it fluctuating quite significantly across the recording. And on the right is the analysis output that we got. So it shows that the electrode connection check that we got, it looks good as the quality score is like 0.81 out of 1, which tells that the electrodes were well placed. The average heartbeat rate is around 59.3 beats per minute, which is just on the edge of normal. And the max had hit like 181 beats per minute at one point, which is quite high. So the algorithm just flagged two findings. One is mild bradycardia, where the heart rate dips just below the 60 BPM threshold, and more significantly, a possible atrial fibrillation flag where it shows, which is based on highly irregular RR intervals. So this just pushed the overall risk level to high. So yeah, but like one important caveat in this is that data was collected way before we actually finalized the recording protocol. So the signal conditions weren't actually ideal.
So here, the electrode contact based on the recording that we took was poor. So the ECG waveform, as you can see, appeared distorted and with like a noisy baseline and less clearly defined peaks. So this really reduced the reliability of the heartbeat detection, and it also triggered a warning, as you can see, recommending the electrode adjustment. In contrast, on the next slide, so here the electrode contact was good. So the ECG waveform was much clearer. The R peaks could also be like consistently detected, and this enabled the stable heart rate calculation and even improved the signal interpretation. So overall, the system was successfully demonstrating ECG signal visualization, heartbeat detection, heart rate estimation, and basic electrode contact feedback.
And based on this, we did kind of a quick user interface mockup of what we would
Beautiful.
like our user interface to look like in the future to kind of show what electrode, when we actually get to discern the signal from each electrode, to show maybe green for a correctly attached electrode, yellow for a weak signal, so maybe kind of press the electrode to improve contact, and red would be that the placement is wrong and that it needs to be placed somewhere else.
I hope I'm audible.
Yes.
Okay, yes. So moving on to the path forward, what we want to do in the future is that we want to create something that's more of a complete device and not just a prototype. And so we're going to keep on building on this existing prototype that we have. And in order for us to actually build on a fully functional, independent device, we need to first figure out a way to collect signals from individual electrodes. Because as of right now, we are using three electrodes and they're placed two on top chest and one on the lower side abdomen. And so all of them are connected through one wire, and so we get one signal. What we want to do is to be able to retrieve information from individual electrodes, so then we can say, okay, this specific electrode is not placed correct. You have to move it a few centimeters to this side, that side, something like that. And in order for us to actually say where to move and how much to move a specific electrode, we need to bring in the optimization feedback in the loop. And so we have planned sort of like an experimental design, which we'll discuss about in the next slide. And we would also like to add more pathological detection. As of right now, we're doing bradycardia, which is the slower heartbeat, and then tachycardia, which is the faster one, and atrial fibrillation. And we would like to incorporate other detections as well, such as arrhythmias and so on. And after that, we would also like to make it more sustainable and frugal in general. As of right now, the cost in order to make this entire device is approximately 2,645 rupees, which is approx $28.69. And per person, in terms of three electrode placements, we would have to spend approximately 30 to 40 rupees. And we have to keep on replacing it because it's one-time use. And so we would like to potentially in future change that and move into suction cups, which would cost significantly less amount, and it's reusable, which will only cost like few hundred rupees, so 200 and something. So adding that, the final product the price estimate is 3,044 rupees, which is approximately $33. And so integrate once the device is ready, we would like to incorporate past data sets that we have found, and also collect our own data and then incorporate that and then build on machine learning and or other models out there and fine tune as necessary. Okay, yeah, and then we would like to validate this entire thing by collecting data with an actual fully functional EEG from hospitals and then cross-reference it to then validate our model. So the data collection protocol that we have currently is that we would, as you can see in the circle, there is an optimal position where exactly a specific electrode must be placed. So based on the optimal position, we will then take recordings by moving it certain degrees. We are thinking 45 degrees of rotation, moving 5 degrees across. So that would look something like move left 5 centimeters, and then keep on traveling across the perimeter of the circle with a radius of 5 centimeter of sort, and then keep on collecting information. Then we will use that data set to then learning and or train different models to then say, okay, we are guessing that you're approximately here. Could you move this degree or like this centimeter? So that's what we're hoping for. And in terms of recording times, we are guessing should be able to tell whether it's a good signal or not by just spending few seconds. If it's a bad signal, then we would keep on relocating to find the ideal position. If it's a good signal, we would record approximately 30 seconds to then do all the calculations.
13 minutes. So we have a couple of minutes for questions. Questions from people.
I have a question. Is the electrode more important, the distance between the electrodes or where they are on the body? It's not clear to me.
Because it's a differential measurement. What is more important, to get the accuracy of distance between or the absolute position of individual electrodes?
Yeah,
Yeah,
I
go
can
ahead.
go ahead on that.
Yeah, just
Yeah.
yeah.
So approximately, as long as you place electrodes onto the lower part, I actually have electrodes on my body right now. I was just doing the test. So it doesn't, what matters the
So
most
this
is
is
how
data that
closer
you
you are
guys
to a specific
collected. That's
location.
exciting. Yeah, go ahead.
Yeah, we have collected some data. So what matters the most is that, so for example, if you're supposed to place something on, let's say, right next to the clavicle, what matters the most is that how closer you are to that optimal position. It doesn't really matter too much as to distance between the electrodes because we already have fixated locations. So think of this as an AED kit of sort. When you open it, there will be posters of sort telling you where, like approximately where these colored electrodes are supposed to be. So you already know where they're supposed to be. So the distance between them doesn't matter too much. What matters is how close you are to the optimal position.
Yeah. Other comments? Yeah, Kevin, and then yeah, right here. Go ahead.
So really cool that you're able to collect data and have that UI interface. I'm curious as to more on the hardware side. I know you have a prototype right now, but in the future, if you envision a wearable, I'm curious as to what your thoughts are, how to adapt your prototype into a wearable. Because one of the biggest issues with health monitoring is the consistency at which people and users actually put them on their bodies. So if you want some meaningful health statistics, it's like making sure that users don't take it off or get frustrated with it. One example are like these health monitoring rings that kind of forget about, and that's like the magic, or that's like good threshold for a good wearable, is you don't even know it's there.
I think their use case is a little bit different. Their use case is a screening.
Oh, screening. Okay.
So lots of people come in a primary health center and they get quickly screened.
I see.
So the device is put on and put off, put on and put off.
Okay.
Yeah. But I think it's a good point. I think one of the threads to think a little bit about is transitioning from where you are currently, because you guys are really far out in terms of you actually have something that's working. And so you can imagine designing a usability study. And what would you do between now and a usability study where you try to get a community health worker to make a recording? I mean, that would be a phenomenal test. It's all external. It can actually be done. So what would be the next gap to make sure you could do that? Go ahead.
Yeah, so we actually have been looking into that as well. So we've been coordinating. So 5 of us are from Ashoka. So we've met with the infirmary already, and we've had a lot of discussions about wearables. So there was a conversation about Apple Watches, which use one lead on the wrist, and they measure the heartbeat and so on. So there have been quite a few conversations about that, and also finalizing an age group or something to start getting actual testing and everything done. So we are working with the nurses and doctors in the infirmary to do something.
Yeah, and I think
what we're
what's
really
really
interested in. Oh,
Oh,
sorry.
go ahead, Francesca. Yeah.
No, what we're really interested in is also kind of hearing feedback from primary health workers on how they would like to get the feedback, because we thought that what was interesting is maybe integrating some kind of audio, because maybe readability can be a problem. So maybe having an audio feedback for the electrode placement will be good. So we would probably conduct kind of a focus group situation to hear their thoughts on the usability side.
Whenever I'm thinking about this problem, I'm thinking of a little bit like a Geiger counter. That, just with Geiger counters, with radioactivity, the closer you come, it starts beeping faster. There are all kinds of these audio feedback, and it depends on your feedback loop time. How much time does it take to process, and how much time you need to collect data to say something about it? Because in human kind of feedback loops, if that time is too long, then you cannot, because like, I mean, it's the same problem that some of you, when you go to the shower and you want the optimal hot temperature, but it takes time for the water to change. This is a classic problem that you get this oscillatory dynamics and feedback loops. So think a little bit about that feedback loop. Your compute time can be very, very short, but I don't know, you have to record a few pulses before you can say whether it's a good placement. But that means the user has to go very slowly so that they don't miss out the optimal point by just jumping across. So building something in the dynamics that forces the user to go slowly, maybe. Maybe your leads are quite sticky and you're scanning them, but they only move at a certain rate. Because there's something about continuous nature of this. You have a continuous signal and you have a continuous feedback loop. So ideally, you should be able to match the two. And that would be phenomenal to do some tests on.
Right now, sorry. No, okay, right now
it's
our feedback
go
is
ahead.
only a couple of seconds. So
A couple
for
seconds.
the contact, yeah, for the contact, it's pretty good. We're going to see for the placement how it goes, because placement is a bit trickier. Contact is a bit easier.
Yeah, I was thinking mostly about placement. Okay, Enrico, and then we're gonna switch. Yeah.
I was thinking, instead of individual electrodes, could you have like an array of lots of them that you can just like roughly place, where the heart is, and then
you let go of the problem of placement and
having
you
more heart
infer it more computationally that one of them will land correctly.
Yeah.
Yeah, I think the number of channels increase the cost, but it could be something that could be done, like a multiplexer.
Yeah, similar to the ultimate multi-parameter.
Yeah. Do you see what I mean by multiplexer? Is that your input channel could still be the same. So you still have a single chip, but you can use a transistor to pass through and say, oh, this combination was the perfect one. So you're not, technically all the other electrodes are done. Okay, Ash, reaction to that. I really like that idea. Yeah.
Yeah, so we actually thought about that. So 3 is the minimum kind of electrodes that we are looking at, but then usually people do 12 electrodes, and that's like, many as well, right? But again, the same problem exists, which is that they still need to be placed closer to the optimal position. So when it becomes 12, you also need to take a look into putting one of them in the thigh region, 2 of them near the ankles, 2 near the wrist. And so there's like so many things that you have to look into. And so that is time consuming, and also considering that most of these things are, at least the packs that we're working on right now, are like one-time use. So each of them would cost like 15 rupees. So it'll be like really expensive as well. And so in terms of usability, since we are thinking of potentially sort of like primary health workers, or like people who are not necessarily trained in these technicalities, so it would be a bit difficult for them to look into 12 electrodes. Comparatively, 3 would be easier. So that's why we invented 3.
So Ash, kind of just to translate, my intuition of what Enrico has just proposed as an idea is slightly different. Think of your 3 electrode setup, except every electrode then is multiple electrodes. It's a little bit of a fan out. It gets still put in the same place. So the user is only putting one. But in fact, every one of the 3 electrodes has 5 internal electrodes in it. And computationally, you choose which one you take the signal from using a multiplexer. So at the end of the day, the user doesn't know that there are many electrodes. They see only 3 electrodes, but you have taken the positioning error and distributed it amongst multiple electrodes. And the final readout is still a 3 electrode readout.
Okay,
So
that makes
it's just
sense.
a computational trick. And the question is how much minimum surface area you do need to make a contact. Because if it goes below a certain amount, then maybe your contact is not good. But there might be some optimization there.
Yeah, it's possible we would need to use like 8 suction cups for that to cover like a particular region, because the area would be somewhat of a 3 centimeter radius from the optimal position.
Increase and yeah. But I think it's a really cool idea. You guys should think a little bit more about it, because no feedback is the best feedback loop, where you still get the right kind of measurements. Okay, I think we're gonna switch. We only have 10 minutes. I have a hard stop at 11.